Hi, thanks for coming to this presentation. I'd like to talk to you about our work on modeling the development of counting. So counting is an important example of systematic behaviors. It's one of our first. And what do I mean by systematic? Well, let's illustrate with a common developmental task called the give-n task, where you'd ask a child, can I have 2 blocks? And if done correctly, the child will give you 2 blocks. What makes this systematic is you can ask for any number of blocks. So for example, if you say, can I have 6 blocks, then the child should give you 6 blocks. And you can ask for any number. If you ask for 30 blocks, even though the child has maybe never given 30 blocks before, it should still be able to perform this task if it, is able to count. And children often go through somewhat stereotyped developmental stages where they start off not being able to do the task and are dubbed pre-numeral, and then sequentially move through these n knower levels, where if you're a 1 knower, then you can give 1, but not anything higher. And same goes for 2 knower, 3 knower, and 4 knower. It's notable that at that point, children can often count all the way up to 10. They just can't give objects more than 4. And then there's what's termed a cardinal principal knower, which happens around the time children are able to give 5. And it's a sudden change where all of a sudden they can give as many items as they know how to count up to. And so what this might look like on a schematic where n is on the x-axis and the y-axis represents the age at which they gain proficiency, on the give n task for that n, then you see the sequential progression through the lower numbers, but then a sudden or not so sudden transition to a flat part of the curve where all of a sudden they can give the higher numbers around the same time. And a couple caveats here. There are other counting tasks. The give n is not the only counting task, and there are other proficiencies and skills that can be assessed by the other ones. And also, systematic performance on give n does not necessarily imply any principled understanding. And there's some evidence about this. So the term cardinal principle knower may or may not be what's going on. Our aim is to introduce a model that both displays systematic performance on the give n task and resembles the human developmental trajectory. And it's based on a model that was published this year at ICLR called the Emergent Symbol Binding Network, which was created as an attempt to achieve systematic generalization on a number of simple tasks. And I can illustrate just with the first most simple of these tasks, which is the same different task. You're shown 2 stimuli, and you just have to say, are these stimuli the same or are they different? And systematicity is tested by using stimuli that the network had never seen before from a large set of possible stimuli. And the way this network works is it's sort of split into 2 sides, where on the right side here is the stimulus side, and the left side is the controller side. And so at each time step, a stimulus X is given to an encoder, which produces an embedding Z, and that embedding is stored in a memory where there is a set of values. And corresponding to each value, there's a key. And the controller only interacts with the keys. So at each time step, the controller will first write a key to memory, but also importantly, read a key from memory. And it does this reading by computing a weighted average of all the keys in memory. And the weights for that average come from the similarity score between the current Z embedding and all the values in memory. And so this network succeeds very well on all these tasks in a systematic way because it can't actually see the stimuli themselves. It only interacts with the keys based on the similarity scores between stimuli. And what I would propose is the give n task is a modified same different task in the following sense. Let's say the sequence of stimuli fed to this side of the network start with the instruction n. So if this is give 2, you would give 2 to the encoder at t0. And then at t1, you would give the stimuli for 1 and then just count through the count sequence. And so at t2, you would give the network the number 2. And at T0, in order to solve this task, then the network should grab an item. At T1, it should also grab an item. And at T2, it should stop, because here 2 is the same as the instruction 2. And I'm going to show you 3 models for the give-n task: an ESBN model and 2 baseline models, one that just uses an LSTM without memory and one that uses a transformer. And these models will be trained with reinforcement learning, just because there's many different ways to grab items, and intuitively kids often get reinforced when they're learning these tasks. And so this is the setup. On each trial, first we select an n for the give n task between 1 and 10. Then we randomly place a number of objects between n plus 10 and 35 objects among 40 possible slots, where objects are represented by 1s here. This is so the network can't memorize what to do, because the space of arrangements is so large. And then we train a policy. Given an instruction n, it has 40 actions to choose, 1 for each slot, and 1 action to end an episode. So for example, if you asked it to give 2, it should select 2 slots with a 1 in them, and then it should select the stop to indicate it's done the task. And this network is trained with the simplest policy gradient algorithm, the reinforce algorithm. So a bit more detail on the models. First off, we use this pre-trained counter for all of the models, and this is what produces the count sequence in time, as well as the instructions. So at time 0, we have a 1 hot that indicates the instruction n, x sub n, and that's given to an encoder that produces an embedding, z0. At time equals 1, we ourselves feed the network x sub 1, which is the 1 hot, representing the number 1, give that to the encoder, and that will produce a embedding z1. And then for every subsequent time step, we will give these embeddings to a successor function that's been trained to produce the next z embedding. Basically, this is how the counter goes through the count sequence. And so how this would work with the ESBN is these z's represent this zt over here. And you can see that the values in memory always start with z0, the instruction embedding, and then z1, and then z2, and then z3, and then zt. And the way the network should solve this task is basically just recognize when this instruction key, which is the key that is next to the instruction embedding, is read out by the LSTM, because that would indicate that the ZT matches the Z0, or they're the same. And that similarity score should weight this instruction key highest. The LSTM will read that key. It also, of course, gets the object vector, the binary vector I just showed you, so it knows where to grab. And on each time step, it produces an action AT. The baseline models are a bit simpler. The LSTM baseline simply receives ZT and the object vector and produces an action at each time step. And the transformer baseline receives the entire history of all the object vectors and count embeddings up until now, and then produces an action. So let's look at the performance of these networks. So let's look at the baseline models first. On the x-axis, we have the n for give n, and we trained from n between 1 and 10, which allowed us to have this extrapolation regime, testing on n's from 11 to 15, which the network had not seen before. The y-axis shows the accuracy. And you can see, first off, the baseline models do not extrapolate. They do quite well for n between 1 and 5. And there are 2 bars because, for example, with the LSTM baseline, the light bar indicates the best performance of the network at any time on that n, whereas the blue bar indicates the performance of the network on that n when the network was doing its best on average. This is just because the LSTM baseline sometimes learned give 6 and give 7, but then forgot them later on. So that's illustrated here. So both of them fall off in performance after about n equals 5. The ESBN network does very well on the training set and also displays extrapolation. So let's look at the developmental trajectories. If you look at the baseline models, here, the n is on the x-axis, and the episode at which the models reach 66% accuracy is on the y-axis. Compared to the ESBN network, these models take much longer to achieve performance. And if you look at the inset on the ESBN network, you also see something that is, a bit familiar to that schematic that we might expect, where there's this flattening of the curve where the higher numbers are achieved around the same time. So far, what I've tried to show is that the ESBN network displays systematic performance on the given task, and it also resembles the developmental trajectory. We can ask a couple more questions about the systematicity. So for example, at what end does extrapolation start? Let's say we only train the network on give 1, 2, 3, and 4. And that's indicated on the x-axis as the highest end presented in training. Will the network extrapolate? The y-axis here shows the extrapolation accuracy over the next 5 unseen ends. So for example, if the network has only seen up to 4, it does not extrapolate. But with enough exposure to higher numbers, around 5 or 6, the network starts displaying extrapolation. We can also ask what key is being retrieved as a sanity check. So on the left, we have the correlation of the currently read key to the instruction key. And on the right, we have the correlation to all the other keys. And on the x-axis, this is the time step. And on the y-axis, it's given. And what this shows is that at the time when the network should say stop, because it's completed the given task, the correlation is very high to the instruction key along the diagonal, while it's low to the other keys. We can also ask, do the hidden layer representations of the controller reflect this systematicity in any way? And so we have the ESBN network and we have the LSTM baseline. If we look at the first few principal components of the hidden layer and color them by whether the network said stop or whether it continued, of course, you can see that there's a clear separation there because the network either stopped or it continued, and there should be a way to see that. But the question is, what caused the networks to stop? And so you can color these points in various ways. So for example, by whether or not the current count embedding matched the instruction, or based on what the actual time step of the action is, or based on what the identity of the count embedding was at that time. And what you see is that whether the ESBN network stopped or continued is basically all based on the match between the count embedding and the instruction. So it's just performing the same different task as we thought. Whereas the LSTM baseline is entangling all these variables together, the match, the time step, and the embedding itself, in order to decide whether to stop or to continue. And one thing I forgot to mention is in our model, we actually softened the constraint in the original ESBN where there was a hard separation between the values and the controller. You see there's this additional path from the count embedding ZT directly to the LSTM. So actually given the option to overfit on these count embeddings themselves, the network still learned a more systematic way to use the keys to solve this task. Finally, we can ask, does the ESBN network, can it get away with a lower capacity? Because one signature of systematic representations is that they're lower dimensional. And so we do see that. So for example, for n equals 10, let's say the size of the hidden layer is decreased all the way until it's only 32 units. At that point, the mean accuracy of the ESBN network is still high, while the LSTM baseline struggles. And all that to say is that the LSTM baseline is probably entangling a lot of variables and overfitting, and therefore needs more capacity to do that. So if I can summarize, I would say the ESBN can learn the give n task. It displays systematic behavior. It learns it faster. It resembles human development, and it requires less capacity. It's also notable that there's an interesting inflection in all the models around n equals 5, where the ESBN starts to perform well and seems to start using the keys as a learning strategy, whereas the baseline models start failing around that point. And we're not trying to support any cardinal principle here. Rather, it's just that systematic generalization can emerge as a kind of procedural competence given the invariances inherent to the architectural biases we choose for our network. And there's some adjacent models that we look at in the paper to discuss that further. For future work, we're interested if this systematicity can be used to perform other tasks as well. So we are currently developing a multitask framework so that we can study some of these other counting tasks that I mentioned earlier on. So thank you very much for your attention.